Hello everyone. Continuously, in this lecture, I want to talk about the measure space. In the previous lecture, I talked about the definition of the measure space and some example of it. In this lecture, I'll focus some the properties of the measure space. The following keyword: in case of finite measure space, we define some terms and many property: excision and monotonocity and continuity of measure. Anyway, I'll talk about the properties of the measure space. Okay, within the lecture and the next lecture, I always supposed X and mu is measure space. Without the condition, the viewer should remember we always the measures we suppose the measure space. Okay, and if mu x is finite, then we can say mu is said to be finite. We are our attention measure, and this measure space is called finite measure space. The definition is so trivial, but B and C is a little abstract. Statement B: for each sigma algebra which satisfies this property. And in the previous lecture, I already said this is no problem because we defined the measurable function. The domain is the set sigma algebra, and the range is the real number. However, we also always attach it the infinite. We can say this is extended real value system. So infinite is also the range of the range value of the range. So this is no problem. Then if we pick this element, then there exists f. This f is subset of E. And this guys is finite. Then we can say mu is said to be semi-finite. Okay? And statement C: if there exists countable family, this here, all the countable family is the measurable sigma algebra, and each measure is the finite. Then if X is consists of union of E and, then we can say mu is said to be sigma finite. I don't know X is infinite value of the measure or finite measure. However, I don't know, but clear point is that each En consists of X is finite. Then we can say mu is finite, sigma finite, and this measure space is obviously called sigma finite measure space. As I already said, the definition, in particular B and C, so abstract. However, when we expand, if we see the theorems of the measure space or the functional analysis, we can see the condition under the semi-finite, under the sigma-finite measure space, these properties hold, and otherwise does not satisfy. So for this reason, the condition semi-finite, sigma-finite measure space is important. Let's see an example of the semi-finite and sigma-finite measure space. Okay, suppose X is the real number and sigma is the sigma algebra, which consists of countable and co-countable set. So these guys, sigma algebra, whose element is countable. Countable is okay, such as rational number and the natural number, which match it in each natural number. So namely number each set can give the number in each set. And co-countable. What is the co-countable? The definition of the co-countable means if A is the co-countable, the definition is the complement. In this case, because of the real number system, R minus A is countable. For example, in the real number system, irrational number is co-countable set because the complement of the irrational number is obvious result is the rational number, and rational number is the countable set. So this is co-countable. However, finite set, what about these guys? 1, 2 is not countable set or co-countable set. The reason is clear. R minus A is in this case is not countable. This is a non-denumerable set. Okay, non-denumerable. So in this case, this is not a finite case, is not co-countable sets. And C is the countable measure. Countable measure is the measure space I studied in the previous lecture. So mu A is given the order, the element, number in element, and otherwise the number is infinite, give the this infinite case just give infinite value. This is also no problem. Always the measure, when we define the measurable function, the range is extended real value system. I want to claim that R sigma C, this triplet is clearly measure space. This guy is semi-finite, but this is not finite measure space. First, the fact this triplet is semi-finite is trivial. Whenever we choose countable set and co-countable set, there we can always make the subset whose member is finite. Okay? So when the definition of the semi-finite, in whichever we choose countable and co-countable set choose, if E is the countable, also it's no problem, co-countable. Whenever we choose these guys is always infinite, then we can pick of F subset E, but the member F, the element F is finite. Whenever we choose these guys, we always find this F. For example, in the rational number, just choose 1, 2. 1, 2 is a subset of the rational number, and this guy is finite. And irrational number, this is no problem if we just this guy's finite. So this the definition, this measure space is semi-finite. However, this is clearly not sigma-finite. The reason is the following statement. I claim something. Somebody says that okay, when the definition of the sigma-finite is here. Okay, remember the definition of the sigma-finite. So suppose the real number is the union of the EI, where EI is the countable set, the collection of the member is the countable, and each is the sigma algebra. But claim is that it is impossible. All of the EI consists of the countable measure. Somebody says this, but this is impossible. So it is impossible for all EI in element is consist of finite, greater than finite, countable set. In this case, M rather than M is in this case this is sigma. Okay, sigma consists of countable and co-countable. So all EI consists of the countable set is impossible. This means at least one of this set, in other words, at least one EI is co-countable set. We should prove this property. Okay, this is our claim. But to begin it, believe this claim. Suppose it is true. This is the fact. It is true. Then how about the situation? Because for example, EJ is the co-countable set. It is impossible. Or this correction is all of the member is impossible countable set. At least one member is the co-countable set. This means mu EJ is clearly infinite. Okay? It is impossible. This is finite. If it is finite, the complement is not countable. This is non-enumerable. So this is the finite case is not countable set. So all of the member is infinite member. But however, this is contradiction. When you consider again the definition of the sigma finite, each member is always finite. But because of the existence of the co-countable sets, this violates the condition. So this is not sigma finite. Understand? The claim, let's see in the claim. Okay, we already know that if but this claim is clear because all of the elements consist of the countable set. Suppose then these guys EI, note that EI is the countable, but according to set theory, the unionized of the countable set is also countable, regardless finite or union of finite or denumerable. These guys still countable. However, compared to left side and right side, this guys is countable. It means because R is equal to unionize this here, R is the countable. But R is not countable. R real number is denumerable. So this is a contradiction. So it is impossible all countable set, a subset of the sigma algebra sigma consists of the countable set. So at least one of the member is consists of the co-countable element. This is contradiction, violate this condition. So these guys not sigma finite. So in conclusion, X R sigma C is semi-finite measure, but this is not sigma finite. Let's talk about some other terms which are related to measure space. A measure space X and mu is called the complete if M contains all subsets of a measurable set of measure 0. So this means if M is the sigma algebra, then the sigma algebra is always contain all of the measured data set. However, depending on the component of the sigma algebra and the measure space, in some case, these guys does not contain all of the measure zero sets. Okay, let's see an example, which not the complete measure space. Borel sigma algebra generated by the open intervals of real line. It is simply put, we can understand Borel sigma algebra. The sigma algebra consists of the Borel sigma algebra. In the previous lecture, I defined the Borel sigma algebra is the smallest sigma algebra containing open interval I. So in this sigma algebra, at least all of the member BR Borel set is contained open interval. Or whenever we choose the sigma algebra in Borel set, this contains open interval. Okay. Then this is not complete measure space. The reason is clear. In the lecture 12, we defined the measure 0. The set E is the measure 0 means in the subset cover there exists the cover collection of the cover IN such that these guys covered E, and the total length of some of the total length is less than sigma algebra. In this case, based on the definition, countable sets such as the rational number, natural number is clearly measure 0 set. Okay, so for example, rational number is clearly measure 0 set on the real number. On real number. Based on this measure definition of the measure 0. However, rational number Q does not contain the Borel set. This is clear. Because Borel set is the smallest sigma algebra containing open interval I, although the definition of the open interval, but the rational number is in fact even not interval. When the definition of I certainly introduced the definition of an interval in the previous lecture. So rational number is clearly not interval. So open, closed, to determine open or closed is no meaningful because this is not the interval. However, Borel sigma algebra is the sigma algebra at least the least condition is contained open interval I, but rational number is not interval because this is clearly measure 0. However, this set is not contained. So this is Borel sigma algebra generated by the open intervals of real line is clearly not complete measure space. The remark I want to talk about, in fact, this measure 0 is definition of the here. Then we know the definition of the measure. Now, the measure is the set function given the domain is the sigma algebra and goes to the real extended real number system. Then in this case, Q is measure 0. We can say mu rational number is clearly 0. Then the question, what is the mu? Which measure? Mu. In fact, this is called Lebesgue measure. Lebesgue measure just nearly approach in our institution. The Lebesgue measure is the length. However, I will later define the Lebesgue measure. Lebesgue measure, in fact, just if, for example, easier example, if mu a b is given, the definition is just the length, because of the Lebesgue measure is to estimate the length, it's just b minus a. However, more the detail, more precise definition of the Lebesgue measure, I will later define the Lebesgue measure, which we should know the definition of the Lebesgue measure. It is better if we understand the Lebesgue measure. It is better to understand the outer measure, how to construct the measure in the arbitrary set. Okay, so in the definition of the Lebesgue measure, I will later introduce in this lecture. So anyway, we can approach this here measure 0 definition with the measure 0. In fact, this definition is corresponded to the definition over here. It corresponds to the Lebesgue measure. Just estimate the length of the set. Okay. And let's go back to the remaining definition E. This definition E is very important definition. This is also in if we run the functional analysis of the measure theory, the condition almost everywhere in X is always emerge. The property P, this is the mathematical property, is said to be hold almost everywhere in X. Shortly, many others use A point E on X. The definition is if there exists a set N is the element in sigma algebra, this satisfies measure 0. So if a sigma algebra is measure 0, then the property P still hold the sub X minus N. So complement N has property P. So if the property P, mathematical property P exists, this property also satisfied accepting the set N, which is the measure 0. Let's see an example of the almost everywhere. If f, the closed bounded interval, is the monotone function, then f is differentiable almost everywhere. This means except from the measure 0 set, this function is integrable. Let's see this example. In the previous lecture 13, I explained this graph. Even though the formula is really complicated, but I think that this is a good example to explain this description. In this case, plotting this graph, this continuous point, this 1 over 2, or half, and 2 over third, and third over 4, and so on. Note that this continuous point is let's set M is the sequence AN which satisfies these functions to infinity. Then because this continuous collection of this continuous point is clearly countable set. So this set is measure 0. In the previous lecture, in the lecture 13, countable set, correction of the countable set is measure 0. This is clearly countable set. This is measure 0. So except for measure 0 point, this monotone function is differentiable. Then we can say this situation, f is differentiable almost everywhere. From this slide, I want to introduce the theorem of the measure space. In the previous slide, I explained the definition, some definition of when using finite measure space, such as sigma-finite, semi-finite, and frequently used term complete measure and almost everywhere, and so on. Okay. In this slide, I said the theorem, the measurable space. Even if you construct any measure space which satisfies the condition, this property is always satisfied, no exception. The first condition is the monotonocity. If A subset of B and clearly AB in the measurable sigma algebra, then this mu B is greater than mu A. And excision property, if A is subset of B, and I forgot, A, B is also A and B, both of A and B is sigma algebra, and mu A is finite. This condition is essential. Then mu B set minus A is equal to mu B minus mu A. And last condition is countable monotonicity. For any countable correction is given, and these guys covers the set E, then of course E is the sigma algebra, and these guys also sigma algebra. Then this inequality are satisfied. If we believe the monotonicity, then it would be mu E is smaller than, because of monotonicity, this here. But surprisingly, this set, rather than this and this inequality are satisfied. Then let's prove the statement A, B, and C. Relatively both of A and B are easier than the statement C because the length of proof is short. Anyway, the important keyword to prove the statement, the theorem, is utilizing the definition of a measurable function. This mu is clearly measure or measurable function, and measurable function satisfies this condition. And the most important keyword is countable additivity. If this joint set is given, then we can change the unionized form into the sigma summation form. So, idea is construct the disjoint set in the given condition. So, prove statement A. In the given condition, A subset of B, we can say B is expressed as A union and B minus A. Then note that A and B minus A, each set is disjoint set. Anyway, we can say mu B, because this is equal, we can say mu A union B minus A. And because this is disjoint set by the measure, then because mu is measurable function by countable additivity condition, we can express summation form mu A plus mu B minus A. And note that we can say mu B, again I expressed mu A plus mu B minus A, and note that all of the measure is positive. So if we consider mu B A vanishes, if these guys vanishes, clearly this value is greater than mu A. So the monotonicities are satisfied. And we also induce the statement B, excision property. Just in the given equation, just this value mu A, just move the left side, we can deduct the excision property. But important point is that to satisfy the excision property, mu A is finite. Okay, so the assumption mu A is finite is essential. If not, otherwise, if mu A is infinite, by the monotonicity condition, note that A, because A is subset of B, mu B is B. Some say, oh, this is no problem. Why the monotonicity condition has finite condition is not? Why the finite condition does not contain the monotonicity? This is no problem, because when we define the measurable function, the measurable function's range, mu, the range is, I already said, extended real value system. So even though mu A is infinite, mu B is also infinite, and infinite it is equality, as so there's no problem, because we define the measure space in the extended real value system. However, if this condition vanishes, the problems occur, because I said mu, if this is infinite, then I said this is infinite, and this equality satisfied. This is infinite minus infinite. This is indefinite form, indeterminate form. So this value is not defined in the extended real value system. This is does not satisfy. For this reason, the equation, this condition is essential to satisfy the excision property. Some says, oh, even though mu A is finite, when it comes to mu B can be infinite. This situation can occur, because even though A is the finite measure, then B is no warrant to finite measure. So mu B can be infinite case. But in this case, this does not problem. In this case, then if mu A is finite measure and mu B is infinite, then this means infinite minus, if this value is the A. But this is no problem, just defined. This value is well defined. I don't know currently the extended real number system, but in Wikipedia you can see this definition is well defined. So even though mu A is finite and mu B is infinite, this is no problem. However, if it's mu A is infinite and mu B also infinite, in this case, infinite minus infinite. This is because this is not well defined. This excision property does not hold. So because of this, mu a is finite condition is essential property to satisfy the excision. Prove the countable monotonicity. The idea is same as we did prove the excision and monotonicity, but I said the proof is a little complicated than the previous theorems. Anyway, let's dig in. The given set, consider the set E is the measurable set, and on the assumption this E is covered by the En. So, however, the idea when considering the disjoint union, I define the new set GK, which means if K is 1, I define this E1. So, for example, E1 is given. This is cover of E. So anyway, E1, G1 is just E1. However, when K is greater than 2, I define GK is EK minus set minus unionized I1 from I1 to K minus 1 and EI. The definition is a little complicated, but for example, in case of G2 just E2, this is just a single union, E1. And G3, in case of G3, is E3 minus unionized, in this case, E1 union E2. Why we take this test? The reason is to construct the disjoint set. Let's see this case. When considering E2, E1 and E2 is given, then when you consider, I can see this here. This is the intersect E1 and E2, and when considering G2 is just here, except from the intersection point, just this is G2. This here. And when considering the E3 is better if each set is disjoint, but in general, maybe this when considering our considering case, this case would happen. In this case, E3 is given, then G3 means here. This slash is G3. Is it G3? This means given the E3, the intersecting point E1 and intersect E2, E1 and E3, this here, it vanishes, and E2 and E3 is also vanishes. So G3 is only the slash line. This here. So when considering this cover in the same principle, we can construct each cover is disjoint. So in case of E1 is here, consider the R slash is not overlap here. Okay, E1 is here and E2 is here. E2 not contain the intersect point E1 and E2, and E3, in case of E3, this slash does not contain this E1 E1 intersection E3 and E2 intersection E3. So when it comes to new set GK is the process each cover union each cover E1, E2, E3 all disjoint, and verify that unionize EK. EK is just a cover. So this here, E1 and E2. E1. Alright, another color. What is better? Here, E1, E2, and E3. Unionize these guys is same as GK. This intuitively this is clear. EK, and I consider EK is here, 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 and GK is the here, 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 but GK is disjoint unionized. So this blue slashy and purple slashy and the green slashy is total. In fact, is as good as EK. So just the difference is the how to unionize this union, how to unionize the set. This is just the arbitrary covered union, and this is disjoint union, each cover. Construct this as DK is each cover is disjoint. Okay, and note that in generally, because the process of GK is get rid of the intersection point, so mu EK is generally okay, mu GK, its correction of this joint set is smaller than mu EK. Also, we can deduct countable. This inequality resulted from the monotonicity. In fact, EK, we consider GK and EK is generally dissatisfied. E1 is the blue cover, and in this case is the same. Okay, in case of G2 is just this slash, and E2 is this blue cover, purple cover. So the counter monotonicity property, this inequality are satisfied. Then we can ready to prove the counter monotonicity. Why? When we start mu E is clearly because this here countable. This is monotonicity condition statement A. This is clearly this inequality satisfied, and this from this here, this is mu I minus 1 GK. Okay, and each GK is disjoint. Okay, so we use the countable monotonicity. This is mu GK, and again, each the monotonicity condition, we can say sigma mu EK. So when considering the here and here, we prove the countable monotonicity condition. Again, let's see some remarks which is related to the previous theorem. I previously defined the sigma finite and semi-finite. Okay? Sigma finite and semi-finite. And I previously every semi-finite sigma algebra, a semi-finite measure space is not sigma-finite. So this is first. When you considering previous example, on the real line, the measure is collection of the countable and co-countable set, and the measure is the countable measure. Then this is not counterexample. So semi-finite is not sigma-finite in general. However, every sigma-finite measure can be semi-finite. So I prove the statement. Suppose the measure space is sigma-finite measure. So this means clearly countable family exists. There exists countable family xj. J is this 1 to infinite. This is countable family. And each measure is, whenever we choose this cover, this is finite. And x is generated by unionized xj. And now, to prove the semi-finite, let's assume that E is a sigma algebra element, and E its measure is, only the assumption is infinite. Our claim is obvious. We can find the subset of F, which is measure space with sigma algebra, but this F is a finite measure, but not zero. We can find, our claim is to find the set F. To find the subset of F, let's consider EJ, the set E expressed EJ, which is EJ is cover. So consider the cover E is unionized EJ, but EJ is as good as X intersection XJ intersection E intersection XJ. So if we describe this situation, E is subset of X, and mu E is the infinite. If X is finite, clearly mu E is finite. Then this is viscously true, because the assumption is first. So in general case, so X is infinite case. Let's consider X is infinite case, and this X1 and X2, this is covered to cover X. I cannot describe the cover. Anyway, X is covered by these guys, X1, 2, 3, Xn. Okay, and EJ means where is E is here. This is subset of E, and EJ is unionized EXJ. So E1 is here. This is E1. This is E1, and E2 is here. What is E2? This here, this. 해주세요. This is E2 and this is E3. In this way, in case if E and X and disjoint, this is just empty set. So just overlapping point, correction overlapping set, overlapping area, we unionized this construct the set E, which is constructed by E intersection Xj. This which can be the cover of E. Okay, and let's go ahead. My claim is here. Each EJ correspond in this statement F. So EJ, clearly EJ is subset of E, and this for each J with mu EJ is finite. We can find EJ satisfy this. If EJ satisfies this condition, mu can be semi-finite measure. I already forgot. As I said, EJ is subset of E. This is clear statement. So our claim is which each index J satisfies this each EJ, mu EJ is positive but finite measure. The observable point is that clearly by the definition of the EJ and intuitively the diagram, this is E1 and this is X1. So clearly using either or the definition of EJ or intuitively the diagram, we can find EI is always subset of the XI for all in this J using the index J or J. Then in the previous slide I explained the monotonicity. Because the monotonicity property mu EJ is less than mu XJ. Then note that by our assumption, because this measure space is sigma-finite measure, so our index Xj cover Xj satisfies this condition. So this is finite. And from here, we can check that mu EI is finite. So these equalities are proved. Inequality are satisfied. Remaining point is that this here. To check this, let's suppose mu EJ is 0. Then mu EJ, rather than here, check that because mu E is infinite, clearly this is true, and E is expressed this here. This is also satisfied, unionized EJ, and also check that this is this is larger than here. In these equalities are derived from this mu. This here in the previous proof, the counter monotonicity, this is this. Okay, these equations are satisfied. So because of this, these inequalities are satisfied. And note that because all index j is 0, this I mistake. This is all of j is the mistake. Ej for index some j dissatisfied. So my assumption is that suppose mu ej 0 for all index j. Okay, so we can find there. Our claim is to find some element j. So this is the better. Our assumption is for all, if all elements index j mu eij 0, then this is also, because mu eij is 0, all element mu ei is 0. So this summation is 0. Then this is a contradiction our condition, because this implies 0 mu e is rather than greater than 0 and less than 0. So mu e is 0. However, mu e is infinite. So this is clearly contradiction. So this, from this here, the blue box is also true. So there exists ej for some index j such that these properties are satisfied. The measure space is semi-finite. Every sigma-finite measure space is semi-finite measure. Let's see another remark. We introduced the definition of the complete measure space, but using the monotonicity, we can redefine complete measure space differently. In fact, this is the equivalent relation, but I think that this definition I want to introduce is better than just this definition. As we know, this condition is property even if any measure space construct. Even if you construct any measure space, this property is always satisfied. So using this property, we can redefine complete measure space. The definition is here. Consider M is the sigma algebra, and suppose the N is the element such that mu N is 0. It's 0, measure 0 set. And consider the another subset of the M. M is subset of the N. This is a fancy text alphabet. This is sigma algebra. This M is just a subset of N, an element in sigma algebra. Then, if this assumption is given, then if M is also the sigma algebra, then we can say this M is called complete measure space. This is clear when observe this here. Because M is subset of N by the monotonicity, mu M is less than mu N, and mu N is 0. So this implies, because the measure is always function is always positive value or 0. The domain is real number plus is here. Okay, we define the mu. Okay, mu, the value is always positive, including 0. So mu m should be 0. Okay, so the complete measure space that define all measurable sets. Sigma algebra contains all measurable sets. So this precisely express every measure space, every measure zero space contain. This sigma algebra contains all of the measure space. The last slide I want to talk about is the continuity of a measure. Prior to this, I will define some terms: ascending and descending set. If these guys say to be ascending, means ek is subset of the ek plus 1 per each n. When describing this situation as a Venn diagram, the index, the more the index is increased, the set is larger. So here. And it is because this equality is contained, in some case this is the same and another is the same. This is the definition of ascending set. Ascending. And in other ways, this if the set of the sequence is the descending, means ek is superset of the ek plus 1 per each n. This means also describing the Venn diagram. If E1 is given and the index, when the index increase, the set is shrink. So E1, E2, E3, E4, and so on. Then continuity of measure theorem is here. For any ascending family ek of measurable sets, we have this equation, we obtain this equation. And in case of the descending case, and this in this case, this condition is essential. Anyway, if this condition is given, then this equation, we obtain this equation. So ascending and descending case, we get the formula. This said continuity of measure. Let's prove the statement continuity of the measure. But statement A left to the exercise. I'll prove the statement B. The fundamental and essential idea to prove the continuity of measure is also how to construct the disjoint set, as we proved the monotonocity and excision and countable monotonocity. Okay. In the philosophy, I define the new set dk. What is the dk? Dk is given. K is positive and including the 0. So if k is the greater than 1, this set is ek set minus ek minus 1. For example, if we describe D1 is E1 minus E2. So the result is here. E2 is the here. So E1 is this here. And similarly, we can define D2 and D3. So if describing the task D1, D2, D3 is here. We can check that each DI and DI and DI are disjoint. Disjoint set. Okay, and if K, what is the D0? Because K is including 0. If note that this sequence E1, E2, E3 is decreasing. So when considering this, we can define this here. This is intersection of all EK from K to 1 to infinite. Okay, we define the decay. And note that we expressed the mu E1. Mu E1 is the whole set. This here, the biggest set. Yeah. However, note that forget mu E1 is the finite. Under the assumption mu E1 is finite, if this condition vanishes, the continuity of measure in decreasing case fails, whereas the ascending case. Okay, so the finite value mu E1 expressed as, because mu E1 is unionized D1, D2, D3 disjoint set. Okay, mu E1 is the whole set in this here, containing this inside. But mu E1 is mu E1 express D1 union D2, D3, and so on. This set is disjoint. Note that. So this is mu di. From the notation problem, I say the dk from K1 to infinite. And because I said this is disjoint set by the countable monotonocity, we can say this is mu dk. And note that if we just to convenience to prove, I'll say this is D0. What is the D0? I forgot this. Start from 0. Okay. This is K to 0 and infinite. So we can say this is mu 0 and the sigma, another case, K to infinite mu dk. Of course, K including K0, this erase the disjoint, this D0 and other element are disjoint when defining the dk. Then, because D0 is expressed the intersection of a union, we can express this is intersection K from 1 to infinite EK. And this, note that this, because this K starts from 1, we express the K as the set minus from. So, and the definition, using the definition of the infinite sum, we can express this is the limit n goes to infinite mu e k then minus e k plus 1. And note that this satisfies, because this is finite, mu e1 is finite, this case we can express by the excision property. Excision, the main property I remarked in the measurable function. Excision property, we can express the yellow on the line is mu. This contained the sigma. So limit n goes to infinite, sigma k 1 from n mu ek minus ek plus 1, and this property by the excision. Thus, because of summation, we can eventually express mu e1 minus mu en plus 1. And note that this is all connected to the equation. So I delete here. Mu e1 is the intersection of ek and limit of mu e1 minus mu en plus 1. And note that this does not affect the infinite, and this value is convergence. This is trivially convergence because I said that mu e1 is finite, okay? So, and this is descending sequence, so this is a satisfies. So, and note that when n is bigger, n is the larger, this value is shrink. However, mu e1 is finite, this value should be convergent to some values. So we can expand mu e1 is mu intersection of ek, and this does not impact on the n, so this is mu e1, and this value expressed as limit n goes to mu en plus 1. This value is always convergence because of this descending sequence and monotonocity. And note that this e1 and e1 vanishes. So finally we get the formula continuity of measure in descending sequence. And this n plus 1, we can interchange just en. So the continuity of measure in decreasing sequence are satisfied. So our proof is finished.